In this video, we're going to be studying layers and also demonstrate the PALD module of the product. PALD stands for predictive aggregate loss distributions. You probably know now that when you design a model for your data, the model has two components. It's got the trend structure in the data and also the process variability in terms of distributions. And the model then to project distributions in every cell in the future horizon. Those distributions are log normal and they're correlated. And to find distributions of aggregates, because there's no analytical distribution for aggregates of log normals, we simulate from the individual log normals. So we're going to illustrate that, and we're also going to illustrate a great benefit of this paradigm shift, and that is that layers are related and how they're related, and more on that also, of course, once we introduce the multiple trend family, multiple probabilistic trend family modeling framework, where you can also then study the relationship between the different triangles. So we're going to look at three layers, and here they are. 1M, 1Mxs1M, 2M. So a triangle that we've called 1M, or triangle group that we've called 1M, the paid losses are based on individual losses that are limited to $1 million. So if an individual loss in a particular cell exceeds $1 million, it's actually truncated at $1 million. Similarly, with limited to 2 million, all 2M, each paid loss is in respect of individual losses limited to 2 million. And the 1Mxs1 million is the difference between 2M and 1M. So let's open the three triangle groups. And each one has the same model. What I mean by model, it has the same parameter structure, and that is that it has parameters in the same periods. So I can run, say, the good model here. Doesn't have the same parameter estimates necessarily. The good model for this triangle and the good model for this one. If I tile vertically minimizing regression tables, if I look at the residuals, if we just examine the residuals versus calendar year, you'll see that they're very highly correlated, and in a subsequent video we'll actually calculate the correlation and we'll design one model that also relates to three triangles. You can see, for instance, the 97 calendar year is low in this particular triangle. It's also low here. It's also below the zero line mainly here. So let's get rid of these residual displays and now focus on the three model displays. You can see that same structure because I've used the same model. Not only that, the parameter estimates are also very similar. I mean, if you look at the development year trends, they are very similar. If you look at the accident year changes, again, very similar. Oops, let me show you the accident years. Lost a bit of concentration there. Okay, I mean, there's a bit of a drop there. There's a bit of a drop there. There's no drop there. Okay, what about the calendar year trends? Well, they're not the same. The limited to 1 million has a trend of 10.35% plus minus 3.93. The limited to 2, sorry, that was the limited to 1 million. That's the limited to 2 million has a trend of 8.7 plus minus 4. But the 1Mxs1 million has an insignificant trend. Okay, I mean, when you model the three triangles together, then you'll get a more precise estimate of this trend. At the moment, it's imprecise. So let's look at the following scenario. Suppose now that you're the reinsurer, and the cedent comes to you and says to you, can you price for me losses for the next underwriting year limited 1 million excess $1 million? And they only give you that triangle for which the paid losses are in respect of individual losses 1 million excess 1 million. And you model that data and you find out that this calendar year trend is insignificant. 5.63% plus minus 4.33%. If I optimize this model and set that trend to 0, it will have better discriminatory statistics. But I could be making a mistake because you're looking at a higher layer. The process variability is very high, so you could actually argue that there is a trend in the data, but because the process variability kind of swamps the trend, there's a lot of volatility around the trend, I don't have a precise or credible estimate of that trend. If I had the other two pieces, limited to 2 million and limited to 1 million, I would get a more precise, so I'd be doing sort of formal probability weighting in the composite model, and I'll get a more precise estimate. But you don't have the luxury of the other two triangles. So you should just stick to that. In other words, when you do your projections, you're going to argue, I don't know the trend, but I am assuming that the actual true trend is a random number from a normal distribution with mean 5.63% and standard deviation 4.33%. And that's one of your assumptions that you make in your projections. Now, to set it to 0 in the absence of any information that will actually give you more certainty about the 0, I think you could be making a large mistake, and you could be underpricing, and as a result of that, losing a lot of money. Now, if I were to simulate a number of triangles from this model that had this amount of process variability, which is huge, you know, we also have normal distributions, right? If I were to do that using this trend of 5.63% in most of the simulated triangles, the estimate of the trend again will be insignificant or non-credible. Okay, so that gives me more evidence that I don't really know the trend. There could be one there, and I'm going to assume that it comes from this normal distribution with that mean and that standard deviation. For fun, let's just do a projection for the next 3 or 4 underwriting years and also create a combined table. Let's see how many calculations, what are we actually producing here, what kind of tables? Well, this is a combined table. It also has the future underwriting years that start in 1999. And you've got distributions. These are all log normal distributions, mean and standard deviations. These are calendar year aggregates, and you've got your accident year aggregates on the other, in the columns here, on the other side of the table. You can also look at the forecast, the reserve forecast table, which is just the current underwriting year and prior years, and you've got the future accident period forecasts. Well, it's just the future by development year for every cell, calendar year aggregates, and then the outstanding of the total cost distribution or the ultimate for each future underwriting years. It's similar with the forecast summary. You have the reserve forecast summary, you've got the future accident year forecast summary, and you've got the combined forecast summary. Let's suppose instead, just to get rid of some of the tables, but we're still going to illustrate the same ideas without any loss of generality, why don't we just forecast 1999, just 1 year going forward in terms of pricing years. So now we've got, this is the future. Now each one of these cells, our prediction is a log normal and they're correlated. If you just want some more information on the correlations, these are the correlations in these distributions. That's the correlation distributions between the different development years. So development year 6 is correlated to development year 0. That's the correlation in those log normal distributions. Now, I want to know the distribution of the aggregate. I know that the mean of the aggregate is 46.9 million. Let's just say 47 million. The standard deviation of the aggregate cost for the next underwriting year for losses 1Mxs1M is 20.3 million. Let's say 20 million. But I don't know its distribution. So how do we determine the distribution? Well, we know the distribution in every cell and their correlations. So we do a simulation. As I've said before, there's no analytical distribution for aggregates of log normals. And that's the kind of thing you also have with Brownian motion or geometric Brownian motion. So what we're going to do is we're going to simulate from every cell, maintaining the correlations, until we simulate from the 14 cells, numbered 0 to 13. Then we add up all the numbers, all our simulated values. And we have one simulation of the aggregate, and we're going to do that 10,000 times, say. So we go to the predictive aggregate loss distributions, and we're going to do it for future underwriting years. We're going to do 10,000 simulations of the whole year, which is, say, 140,000 simulated values from log normals, because we've got 14 cells. So let's do that. Let's look at the simulated values by exit in Cube, and now let's look at the simulated values by calendar years. Each calendar year only has one cell. And now let's look at the distribution of the 10,000 values for the total that has a mean of 47 million and standard. You notice the numbers on the right of the mean is represented by the red line, are much further away from the red line, but those numbers are less. I mean, that's the property of a skewed distribution. If we try and fit a log normal, it gives you a pretty good fit to the sample values that came from those log normals that we aggregated, and that's the log. The gamma doesn't give you a good fit. We can look at quantiles. Quantiles are the same as percentiles, and value at risk. This is a quantiles and value at risk table. For instance, our mean of 46.9 million, it lies between the two red numbers, these two red numbers, and therefore it's between the 58th and 59th percentile. Interestingly enough, you know, there's a result in probability theory. It's a very old result due to de Moivre, the French mathematician, that actually showed that if you always use the mean as your price, if you always reserve the mean, then in the long run you'll be ultimately ruined. So even the mean is here, 58 to 59%. It makes sense, the 58 to 59th percentile, it makes sense to reserve above the mean if you want some kind of security. If you look at the percentiles or quantiles in descending order, then the 99.9th percentile in the sample is 162 million. That means there were 10 values in the sample of 10,000 that exceed 162 million. I guess that's a catastrophe. If you're looking at the 95th percentile, then the percentile is about 85 million, so your value at risk is $38 million. That means there's a 5% probability that if you reserve the mean of 46.9, so 47 million, you stand to lose at least $38 million. Okay, let's suppose now you want to take some kind of adverse development cover. I mean, we did this on a triangle that is 1Mxs1M, but you can do this on any triangle. It doesn't matter. Let's suppose if we look at the simulated values by calendar year, we're going to use by default two attachment points, the mean, which is around 47 million, and a mean plus the standard deviation, which is around 67 million. So if the total losses for that underwriting year exceed 47 million, as you observe it by calendar year, then the reinsurance kicks in. When it exceeds $67 million, then the insurer, it reverts back to the insurer. So here's the reinsurance. The two attachment points are around 47 million, 67 million, and let's find out what the answers are. And you can see that for the insurer, if he doesn't take out any reinsurance at all, no cover, no adverse development cover, his coefficient of variation is 43%. However, if he decides to take a cover of around 20 million excess 47 million, his coefficient of variation drops by about a third, which is 34%. But look at the reinsurer. He's taking on a huge risk. His risk is nearly 150%. That's his coefficient of variation. And I guess that's what he's there for. If the reinsurer is going to actually take out this policy, then he can recalculate his value at risk, how much capital he now needs to be, say, secure at, say, the 75th percentile. But of course, you have to part with some capital to pay for this reinsurance arrangements. So again, you can try different reinsurance arrangements and see how they work, and then choose something that is optimal for you in terms of, obviously parting with some profit, but also at the same time parting some risk, but having to pay for it. If you look at the simulated values for the reinsurer, let's see how often he pays his limit of about $20 million. Limit, 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 limit. Why is that? Why is it so often that when he pays a limit of $20 million? I guess the reason for that is, if I can find a spare transparency, so why don't we insert another slide. Let me bring up the pen. And the probability that the reinsurer pays his limit of around $20 million is the probability that the aggregate loss exceeds 67, given that it exceeds, say, 47. Well, that's the ratio of the two unconditional probabilities. It's the probability of the loss exceeding 67 and divided by the probability that the loss exceeds 47. Now, we found that the probability of the loss exceeds 47 million. 47 million was around the 58th percentile. So that was about, what was that? That was about 0.42. What's the probability that the loss exceeds 67 million? Well, let's go to our table, value quantiles table, and what will you say? It exceeds 67 million. What's that? It's 86. It's about 14%, say. So you're looking at 0.142 over 0.42, so it's about a third. So a third of the time when the reinsurer pays, he actually pays his limit, which is a lot of money. It's a huge risk, but you need to be cognizant of that risk. Okay, so let's suppose that instead we're looking at the total reserve, and the total reserve in the logbook has a distribution with a mean of 244 million, and the distribution of the total reserve has a standard deviation of almost 60 million. And what you're interested in now is in retrospective cover. So if we look at the forecast table, what we would need to do now, let's suppose you're looking at cover of, say, 60 million excess of 244 million. What we would need to do is simulate from all these log normals, and there's 97 of them, and aggregate. So now we want to simulate the observations from each one of these log normals, and there are 97 of them, maintaining also the correlations. So we go back to PALD and say, go to reserve. Now, if we're going to do 10,000 simulations, we're actually going to simulate from 97. Every time we do a simulation of the whole triangle, we're actually simulating from 97 log normals. So we're doing 970,000 simulations. But of course, we also have to simulate from the parameter uncertainties, because that's an integral part of the model. So we're doing about 1 million simulations. Now, when we do 1 million simulations, we're also going to create somewhere between, I don't know, 50 to 150 tables, displays, graphs, whatever, and let's do that. So that takes about 0.7 of a second, and these are the simulated values by accident year. These are the simulated values by calendar year. Now, some people might argue that simulations are fast because we've got a fast computer. No, that's not the case. The reason the product is very fast, the reason estimation is fast, optimization, the wizard is very fast, simulations are fast because we have proprietary algorithms that are very fast, and it took many years to design. In fact, when we get to the MPTF, we'll be able to model, say, the 40 triangles, 7 triangles that are very large, and we'll be looking at keeping track of, say, 24.8 million correlations, and you'll see that the calculations are extremely fast. So now we can look at, say, the table for the total reserve. This is the value at risk table, percentiles, and value at risk calculations. If you wanted to look at a specific year, you could go to, say, PALD periods, and just look at the distribution for the next calendar year, which is 2004. Is that right? No. Sorry, 1999 is the next calendar year. So that's the table for 1999. Let's do the table for the aggregate reserves. And then you can also do your reinsurance with 2 attachment points. You might only decide to have 1 attachment point, and so on. There's a lot of different configurations here. The proportions taken by the insurer and reinsurer do not have to be 100%. So these are the tables you get. You've also got the simulated values for insurer, reinsurer. You could go back and change the attachment points. Instead of 303 million, why don't we make it 350? So that's 350 million. We've got a different set of tables. It's for 350 million. You can look at the table cumulatively if you wanted to. You do that. ADC setup, is it? Select periods. Let's do it cumulative. So it's cumulative along the calendar years. Now, I'm going to estimate the model again. And after estimating the model, when I do the forecasting, including the next underwriting year, I'm going to remove the parameter uncertainty. That means every parameter that we've estimated in the model, for instance, the 5% plus minus the 4% will be 5% exactly, and so on. Instead of 5.6% plus minus 4, every parameter, in other words, we're removing the parameter uncertainty, and let's see what happens. I mean, do the numbers change? And actually, both the mean and the variance change. The mean reduces, and so does the variance. Not just the variance. Parameter uncertainty increases the mean, not just the variance. So if we now look at the answers for the next underwriting year, the mean is no longer 47 million, it's 43.6, and the standard deviation is no longer 20 million, it's 8.7. So if you remove parameter uncertainty, if a reinsurer removes parameter uncertainty and does his calculations, excluding parameter uncertainty, you run large risks. You run very large risks. When you fit a model to data, the fitted distribution assumes that the parameters that were estimated are the true parameters. The predictive distribution, which we calculate here in ICFIS by default, of course, we can also fit the fitted distribution, which excludes parameter uncertainty. But I think that's very risky. There's a very big difference between fitted and predictive. We have a paper that's that I co-authored, which appears in the Journal of Risk and Insurance, that explains the difference between and the kind of different results you can get when you ignore parameter uncertainty. And I think that Klugman also has a textbook on, I think it's on credibility probably, or distributions, where he explains the difference between fitted distributions and predictive distributions. If you now look at the forecast now of the total reserve, can you see the mean has dropped from 244 million to 35, and the standard deviation of the reserve distribution has dropped from 60 to $18.7 million. Why is it that parameter uncertainty also increases the mean? And you can find this out. This is a fundamental law in finance. It's a fundamental result in finance. And you'll probably find this in most finance textbooks, first year university or first year college. And you can illustrate this to yourself by in the following way. So let me pick up a different PowerPoint display. And let me show you how you can illustrate this, and it's a very simple idea. Think here. Okay, this is a study you can do in your spreadsheet, and it's similar to the relationship between a normal distribution and a log normal distribution. Okay, let's suppose in year 0 you pay $100. In year 1, you pay $100 exponential of I, where I is the inflation rate. In year 2, you pay $100 the exponential of IT, I is the inflation rate. Let's assume that the inflation rate actually is. You're uncertain about the inflation rate, so you're going to assume that the actual inflation, the true inflation, comes from a normal distribution with mean 10 and standard deviation 4.5%. Okay. So what you do, you could simulate, so this is the way you would simulate the payments. Let's just do it hypothetically here. So the first thing you do is you simulate a random number from this distribution, and suppose the inflation you simulate is 0.11, 11%. So you calculate your payments, 100, 100, e to the 0.1, and then 100, e to the point, so this would be 0.11, 0.11 t, whatever t is. T could be 10, so. Then you simulate another opt from this normal distribution, and it might be 0.95. So then you calculate your payment stream using an inflation of 0.95. And so on. And then you might do it 10,000 times. And then if you take the average of these values, it's not going to be 100 e to the point, e to the 0.1. It'll be 100 e to the 0.1 plus a half sigma squared. Sigma squared is 0.045 squared. And of course over here it'll be 100 e to the 0.11 t plus a half sigma squared t squared. And that's what we've done here just as an example. So parameter uncertainty increases the mean, it also increases the standard deviation. So if the average is the same, 10%, the more fluctuation there is in that particular inflation rate, the more you'll pay out on the average. So in terms of the models in PTF, in the probabilistic trend family modeling framework, or the multiple trend family modeling framework, which we're going to study next, an assumption of 10% plus minus 1% is not the same assumption as 10% plus minus 4%. The latter assumption will give you a higher mean, not just a higher standard deviation. So let's go back to the product. So over here we've just studied, we showed you how the probabilistic, predictive aggregate loss distribution module works. We showed you that there's a difference between fitted distributions, which assume no parameter uncertainty. They exclude parameter uncertainty. They assume that the fitted value, the fitted parameter estimate, is in fact the true parameter value. And we also showed you that the relationships between layers, you could see that the residuals were correlated. But of course that we'll then design one model for the three triangles and use the information in each to give us a better idea of the parameter estimates for 1Mxs1M. And the other issue is that if you're only looking one triangle and you only had an information from that triangle, no information from related triangles, and that triangle has a lot of process variability,